Hello and welcome to Embedded Internals. This is seventh episode of our series, a system fundamental series. Today we are going to look into bitwise operation. This is one of the most important episode in system programming, where bitwise operations needed while working with operating system, while working with embedded systems. And we are handling the networking packets in the device drivers, firmwares, compilers. Similar way, we have databases, cryptographies. We know that one integer can store many independent piece of information, and we can manipulate that information based on our bitwise operator. So for example, we know that 1 byte is equal to 8 bits. So all the memories inside our operating system are represented in byte format. So when we are saying 1 byte is equal to 8 bit, and with the help of bitwise operation, we can individually use each and every bit of a byte. Like for example, this is a memory representation of 1 byte, so it is 1 to 7. So like bit 7 can be used for a particular operation, like controlling the read operation. Similarly, bit 6 write operation, bit 5 execute operation, bit 4, let us see, we are controlling timer with the help of bit 4, bit 3 timer 0 or timer 1, bit 2 can be used to control any particular flags. Similarly, for bit 7 can be checked for, let us see, watchdog events, and bit 1 can be used for interrupts. So we have seen how efficiently we are able to manage the memory using the bitwise operation. In this, we have worked on bit level. So all the individual bits we are using for controlling one or the other purpose. And that bits can also be worked for two formats, like either the bit is on or either the bit is off. All the hardware registers uh, we are manipulating inside our code is using this bitwise operation formula only. For example, let us take an example. We have an unsigned char value. Unsigned char x is equal to 173. From the human interpretation, it is just a 173 value inside the memory binary representation. But what machine sees is how the hardware or the CPU seeing is, it is like 1 0 1 0 1 1 0 1. At the end, either the bits are on or the bits are off. So 173, when we are representing or viewing from the machine perspective, it will turn into this. Using the bitwise operator, we can individually control each bit of this value. So bitwise operator are working actually here. Bitwise operator works on binary numbers, binary values, not on decimal or any or numbers in any other format. So we can say each bit can represent something. So if this is a value, when we considered last value 101, so this is a consideration of 3 bit, that where each individual bit for read, for write, for execute. So 3 bit are representing three different operations. Just I will give you how we can convert any decimal format, like we have converted this 173 into this binary format. It is the bit 0 and this is bit 7. So to conversion, it is always like 2 to the power goes in 2 to the power 0. So decimal to binary, we will do multiplication. And it is like 2 to the power 0, 2 to the power 1, 2 to the power 2. Similarly, till 2 to the power 7. 1 is 1, 2 to the power 2 is 2, 4, 8, 16, 32, 64. So we know that one byte range is 0 to 255. For decimal to binary conversion, you are just going to add the value on value on this number. Like for example, 13 can be 8 plus 4 12 plus 1 13. So everything below depends on understanding the position. So it is this is our MSB, most significant bit, whereas this is our LSB. we start calculation from LSP to MSP. What are in the little Indian, we will cover what are little Indians and big Indians, how endians can manipulate our data. We have seen that each bit of a byte can be used for individual purpose, and that can work as a state for either they bit are on at that level, at that value, or off. And in a one byte 8 bits are there, so all the 8 bits can be used for different purpose. Now what all operations we can perform on bit? So first operation is bitwise and this is represented by this ampersand sign, single ampersand. Please remember that logical AND operation is double ampersand, whereas bitwise operations are just single operation, a single AND. So whenever you are working on bit level, we will use this sign or this symbol, bit 0 and bit 1. When we are doing the operations of bit AND, only when both the bits are 1, then only the individual state will be 1. Otherwise, it is 0. For example, bit 0, 0, 0 1 1 0 1 1. Only when both bits are 1, the result will be 1. Otherwise, in case of bitwise AND, result will be 0. So bit becomes 1 only if both bits are 1, and this is the corresponding truth table. Like for example, when I take 1 bit A char, that is 13, unsigned char B value, let us take as 10. When we do the AND operation, 13 can be represented as 8, 13, and 10 can be represented as, so let's perform the AND operation on this value. So 1 plus 0, 0, 0, 0, only this parameter will become 1 because in this case both the bits are 1. So 13 and 10 will become 8. What is the practical use of this bitwise operator? This has done the masking. Only when both the individual bits are 1, then only the resultant bit is 1. So for the masking, we can use this. For extracting any flags, both bit true, so both flags are true. Like this, when we need to extract the individual bits of a flag, we can use AND operator. And for the checking bits, both the bits are on, then the resultant bit is on. So for the checking of the bit, we can use AND operator for the masking and for the extracting flags. Like for the we have seen for the checking bit, that is check if the bit is enabled or not. When we need to check this, we can simply perform AND operation. Like if there is one flag and we need to check if the flag is on at the 4th bit, we can perform the AND operator. 4th bit means 1 2 4, that is 0 1 2. So second bit, we are checking for the second bit, if that bit is on or enabled or not, we can use the AND operation. So AND operation is using practical use of AND bitwise AND operator is for masking, for extracting flags, and for checking if the particular bit is enabled or not. Let us check the code inside terminal. We have taken two variables inside unsigned char A and unsigned char B having the value 13 and 12. We type the statement using the AND statement, or we can say from 0 to third bit, 2 to the power 3, that is 8. So one bit is enabled, so the answer we got here is 8, or in the binary format it is 1000. Let's move to our next topic, that is bitwise OR, represented by this statement. Please remember similar symbol we have in the logical operator as well, and this is for bitwise operation, this is for logical operations on the any decimal values. In the case of bitwise OR operation, rule is same, that bit become 1 if either of the input is 1. So the truth table become, let us suppose we have two bit 0 and bit 1, and this is the resultant bit. So 0 0 0 1 1 0 1, either of the input is 1, so bit 1 is 1, so 1, bit 0 is 1, so 1, both are 1, so 1. Only in the case when both the bits are off, the resultant bit will be. If we take an example having two values like a 12 or let us take b as 3. So 12 in the binary format will be represented as 0 0 0 0 1 1 0 0, and 3 will be 2 plus 1 3. We have seen with when any of the bit is 1, result will be 1. So 1 1 1, with this become 15. 12 or 3 will become 15, that is 1111. In the hexadecimal represented as F. So use cases when we need to set bits, like if any of the bit is 1, we are setting the resultant bit is as 1. Also when we have to combine the bits, like for example in the case of embedded device, when we have to enable permission for any bit, we use this bitwise OR. To enable the permissions for second bit, we will use bitwise OR operation. This is in bitwise OR. Similarly, we have bitwise XOR represented by the symbol this. This is one of the most misunderstood operator we have. The rule applies here is whenever two bits are different, result is 1. Like let us say A and B, and the result is so 0 0 0 1 1 0 1. Both the bits are same, result will be 0. Both the bits are same, result will be 0. Now in the case both the bits are different, therefore the result will be 1. For example, we have, let us take two values, A 13, B is 10. So when we represent 13 in the binary format, this will become, similarly 10 will become this. The rule here applies is when the different bits is there, answer resultant bit will become 1. 13 XOR 10, result will be 7. Toggling bits, if it is enabled, mark it as disabled. Toggle 0 1 1 0, like this. When we have to find the difference between two bits, so it also act as difference detector, while we have to calculate the checksum. Also for the encryption and decryption ideas, mostly we are using XOR operator. So these are the some practical application uses of bitwise XOR operator. Similar to bitwise AND, bitwise OR, bitwise XOR, we have bitwise NOT represented by this. Bitwise NOT means flip every bit. That is, for example, you have a value 5. 5 will be represented as, and when we are doing bitwise NOT, it simply means flip the bits. If it is 0, do 1, 1, 1, 1, 1. If it is 0, 1, do 0. So it is like if 0, flip it as 1. If 1, flip it as 0. So this is like changing all bit from enabled to disabled. So bitwise left shift. Left means left direction, that is this. This operator represent left shift. So example, if we have to 5 left shift by 1. So 5 is represented as 101. Now you have to left shift by 1. So shift this way. Therefore the 1 value will go at the first bit. So it will become, and the last after shifting we will add 0. So similarly 0, so 0 1 0 0 0 0, this value will become 10. 1 bit shifted toward the left side. So often it behaves like when we have an example x, which is equal to x into 2, means this is like a multiplication. But we need to be very sure about the we need to take, while coding we need to take care the situation like overflow. In the case of overflow, bits are discarded. It is a 8-bit operation. We are doing operation on 1 byte. So we need to be very sure, or we need to take care of the overflow condition, because in the case of overflow, bits are discarded. In all the bitwise operator, this overflow rule applies. So we can say bitwise left operator are like the multiplication. It is often like 2 to the power anything x. What is a practical use case of bitwise left operator and multiplication? Any bit level placement, encoding and packing. These are mostly for the networking purpose. When we are transmitting any data over the network, then we have to do the encoding and packing of the bits we are transmitting, and there we can use the shift operations, bitwise right shift. So this means move the bits in the right direction, move the bits in the right direction. So when we have to do 10 20 right shift by 2, so 2 times right shift the value, so 20 will be represented at this. When we have to move the right shift direction, this value will simply, by after two times right shifting, it will become 0 0 0 0 0 1 0 1. These two characters will be shifted toward the right direction. So the output will be like 5. Bitwise right shift operation, like the bitwise left shift is as per for multiplication, it is for division. So formula will become, it often resembles this n, which is similar to x to the power 2 to the power n, where n can be anything. We can say that signed right shift also are there when we are dealing with the signed operators, but they are implementation dependent. Apart from these 6 operators we have discussed in the bitwise, for the bitwise operation, that are bitwise AND, bitwise OR, bitwise XOR, bitwise NOT, bitwise right shift, and bitwise left shift. Bits are also used for bit masking, and in the networking we are mostly using bitwise operator for masking. So what is bit mask? Binary patterns which are used to select bit, only the bit which are required, that can be selected by using this. Like for example, if we need to set any particular bit, clear bit, we have similar logic. Like this, we can use the bitwise masking operator for setting any particular bit, for clear any particular bit. For toggling we can use XOR operator. For check if the bit is set or not, we can use AND operator. How this bitwise masking are using at the hardware level. So let us suppose we have an register, CPU register, always marked as volatile, unsigned int register. So this is a CPU register located at a particular address. We will cover a dedicated episode on bitwise mask. That's why I have just given the preview, unsigned it pointer and any CPU register address. Suppose it is located at this particular address. So when we have to perform any operation like set the particular bit on this register, we can simply use XOR operator. So we are setting 5th bit. This is a register. I want to set the 5th bit of this. So value stored at register or equal to 1. So this is masking provided and 1. So this is like enable real hardware feature. 5th bit will be set in this case. Enable hardware feature, and this is real embedded programming example. To set, we just have a register, memory mapped IOs. So particular address has been registered in our software, and we can play with that register using the bitwise operators. So for any networking packets, either they are IPv4, IPv6 or any TCP, UDP, any protocols we are using, header files or datas are usually bitwise managed. So like if you have 16-bit header, so each bit is performing a particular action. So bits are stored at the data are stored at the bits level, all having the particular permission. Like for the permission we have read, write, execute, and they are at bit level. If this is 7, all the permissions are enabled. If only this means read permission is enabled. If this or this means read and write permission are enabled. If this only write permission are enabled. So we can play with so many combination, three characters and these combination 2 to the power 3. So particular 8 combination. So these are like, this is for the file permissions. Similar way we can use in the networking and embedded devices also. So this is very simple example where I have taken an unsigned int flag, a variable flag having the value 0, and using the XOR operator trying to set the second bit of that. So let's see what will be the output of this. 4. Second bit, 4 means 0, 1, 2, 4 for the second bit. If I will show you this in the binary format, using this logic we are just setting the second bit, second value or third bit. The third bit means 0, 2 to the power 0, that is 1, 2 to the power 1, that is 2, 2 to the power 2, that is 4. So we are setting this as fourth bit. So this is 1 0 0 0 1 2, second bit or third value. So this is how we can set or clear any bit using a particular flag and by doing the bitwise operation. This is an example for right and left shift we by 1, and the value we are doing the operation is bit value 5. So when 5 is left shifted by 1 and right shifted by 1, what will be the answer? That is 10 and 2. So left shift meant multiplication. 5 move to 1. So 1 will be added at the last value. So it will become 0 0 0 0 1 0 1 0. So 5 will become 10. Similarly, in the case of right shift, it is like division. So it is becoming 2. Right? Do one task. Write the binary representation for 5 and try to do the shift operation once, twice, or multiple times and see how the value is getting changed every time. This is just an introduction for the bitwise operation. We will have a particular bitwise operation series where we are going to cover one dedicated episode on each bitwise operator, because this is a fundamental of embedded system. So after seeing the different operators, let me show you what are the common bugs we should avoid when we are working with bitwise operators. So first thing is that logical AND represented by 2 ampersand side and bitwise or bitwise AND represented by 1. Similarly, logical or logical AND. Be sure that what symbol you are using, because mostly when we will use bitwise, for the bitwise operation we need one ampersand sign, logical this. If we will change the symbol completely, the meaning will be different. Okay, sometime we also make the mistake of using OR instead of XOR, mostly when we have to use OR XOR, we need to be very sure of that. This is a very common bug when we are not able to distinguish between logical operation and bitwise operation, and this completely change the meaning of our programming. So we need to be take care of this. Now, how the assembly level coding will be when we are doing bitwise operation. So it is like assembly coding, or we can say how machine is transforming. It's like load any parameter, load any value, perform bitwise operation or bit transform, and then store. Load, bit transform, store. So we have seen that arithmetic changes are quantities, whereas bitwise operation changes only the representation. So now that we can manipulate bits directly, now in the next episode we will going to explore how C control themselves, like measuring objects, converting values, and changing interpretations. Stay tuned for the next episode. Thank you.